Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today I want to talk about super capacitors. So I got a hold of one of these cool kits from Eaton. Has quite a range of them. I'll bring the camera in close so you can look at them real quick. Okay guys, and here's a close-up kind of all the caps. You can see the size of them. I have pretty big hands, I guess, so you can kind of see the size of these things. So here's my box I've had for some years. I got these before they became Eaton, and Eaton swooped up and grabbed this company. They did a nice job with the super caps, I think. Okay guys, so these super capacitors, or ultra capacitors, sometimes referred to, super neat caps, rated in farads. They are low voltage, 3 volts. Now those double capacitors, the double wide ones, they're rated 5.5 volts because essentially you have 2 capacitors in series. So, capacitors like this are low rated in voltage, but farads, lots of capacitance. The other thing with super capacitors is in the past they were always limited to about minus 20 degrees C, but some of these, there's a series that goes down to minus 40. So now they extend down into the colder temperatures. Here, let's just talk about the parameters of capacitors, okay? There's a capacitor. It equals this thing with all its parasitics. Okay, you have some inductance from the leads. Even if you have a surface mount cap, you may have as much as, 5-7 nanohenries of inductance with just surface mount short leads. So through-hole capacitor is going to have longer leads inductance. With capacitors like these, we probably don't care about that parameter too much because they're holding big charge and not. Okay, I guess I gotta take that back a little bit because they can handle, some of these capacitors can handle pulse currents, okay, and that's part of what I want to talk about. These capacitors, like the button cells, this resistor, this ESR, equivalent series resistance that's inside this capacitor, that resistance, it's like 50 ohms, 30 ohms, or even 75 ohms. So that resistor is pretty high ohms. Now, some of these other capacitors, like the yellow ones and the green ones, they're pretty low ESR actually, especially the large farad ones. So that capacitor, so they can actually handle pulse loads. So then maybe inductance would matter something, but probably not. It depends on your application. And then I've shown this resistor. This resistor is essentially the leakage resistor. The capacitor's not perfect. The parallel plates charged up to a certain amount of voltage with all that current sitting on those plates. Well, some of it's going to leak through, and hopefully that's in the mega ohms, right? But now higher temperatures, they actually go up to 85 C, I think they're rated to. At the higher temperatures, this could go up a little bit. So that's something to be aware of, because a lot of times you might choose these capacitors to be backup for memory, or in a clock, or different kinds of circuits where you want to keep the, like let's say an EEPROM or an FPGA, some kind of device that might have memory. You might want to keep that thing powered during power transfers. Maybe somebody's going to swap out the batteries in their product and you want to store a charge there for normal change of batteries. Okay guys, we're going to do a little test, and we're going to do something like this. We're going to take a power source and we're going to close this switch and charge up our capacitor. Then once we charge it up, then we'll open this, and with both switches open, the load not connected, it's going to just sit there and we might leak a little bit of charge off. Otherwise, it's just going to stay there with the charge on it. Then we're going to close this switch and we're going to time it and see how long it takes to drop. So let's say that your memory device runs on 3.3, but it'll run down to 2.5. And so we'll have the load, we're going to use this Siglent Load back here, and we'll have the load turn off at 2.5. So we'll time how long that takes. Now, I just gave some example values of some resistors just to make math easy. If we have 3 volts and we charge this guy up, once we close the switch, current's going to flow this way. It's a series circuit, and it's going to have voltage drops across both these resistors. This is the ESR, the equivalent series resistance, and we're going to say it's 50 ohms just for this example. And we'll say our load our memory chip's 100 ohms. You know, it's taking equivalent current for that. So this is twice the value of this guy. So he's going to drop twice the voltage. He'll have twice the voltage drop. So if we have 3 volts on our capacitor and current's flowing, we'll have 2 volts on him and 1 volt on that. That's not that great, right? I mean, because of the current flow, we're going to be dropping voltage across that internal resistance. So you don't get the voltage across here that you want. Well, our case isn't going to be quite that bad. I was just trying to show an example of why that 50 ohms can be so important. The other thing is, let's say both switches are open, then we close switch 1 and we charge this guy up. Well, when we first close the switch, a normal capacitor with low ESR, it looked like a short circuit. So the voltage here, it almost wanted to short this guy out unless this guy just had lots of available current. But now this guy also has an equivalent series impedance or resistance inside it. So that short circuit, you'd drop most of your voltage across your power source. So right here, you'd have, you know, for an instant, you'd have 0 volts, and then the capacitor would charge up and the voltage would increase up until it became an open circuit. Because in DC circuits, capacitors end up looking like opens after they become fully charged. And when they're an open, you're going to see all the voltage across the capacitor. You won't have current flowing in the resistor and the equivalent series of resistance, so you won't have voltage drop. But with a capacitor with a big ESR, when you close that switch, you'll see 3 volts here. But that's because some of that voltage is across the resistor because of current flowing through it trying to charge up the capacitor. But the capacitor is not charged. We're just seeing 3 volts because we have a voltage drop here and a voltage drop, you know, and the capacitor's starting to charge. But if we close that switch, saw the 3 volts, said, okay, it's charged, open that switch, there wouldn't be very much charge on this guy. So when we're going to test this, and we're going to demonstrate this over here on the bench, okay? So let's do that. But this is an important example because what this tells you is that when you charge up a capacitor like this that you want to have, that you want to use for storage, you know, to keep the memory over here, you have to sit there and charge that for a little while. So if you're testing the circuit out, you power it up, you see the voltage, you go, okay, you open the switch, and you go on. This guy might not be fully charged yet. Remember, these guys are rated in farads. Okay guys, so for this test, we're going to use this power supply, and my switch will be me plugging this guy in and out. I'll just plug it in the power supply and then unplug it when it's charged up. Okay? And then we'll turn on the load and watch how long it takes to discharge. So I'm going to bring you over here to show you real quick. We're going to use this Hubble test meter to monitor the current that's charging the cap so we know it's charged. Because you can't tell by looking at the voltage, guys. You have to look at the current going through it and see when the current's done charging. So that's the new thing about Super Caps. All right, let's bring the camera over and take a look at this. Okay, so this is going to be a simple setup. This lead comes from the power supply. The ground just goes right to the capacitor. Okay, the other side of this is going to the load. Okay, so I've got the load right here and I've got the power supply. Now the positive one, same thing. I've got the load plugged into here, but what happens is first from the power supply we go through the meter into we're going into the milliamp range, and then we're coming out the common to the plus of the capacitor. Remember, there's a little stripe on these guys, so they are polarized. Here, I'm going to hook this guy up, just show you. All I'm doing is connecting them up like that. It's pretty simple. But here, let me bring you down and look at the cells. All right, so here's a little button cell, and you can see the bottom, what it looks like, and the top. It doesn't have the little cross hatches like they usually do, because I think the vent is probably on this side. And there's where the value would be. It says 5.5, 0.33 farad. Okay, and then there's this guy. Now, by the way, I bought these guys. you won't see them look like this anymore. I think this was the kind of when they first merged over to Eaton. When Eaton bought them, they still kind of look blue, but they say Power Store on them, and Power Store aerogel. You won't see that, so don't expect them to look like that, because since Eaton bought them, they put their own, labels on them. But yeah, these are pretty old, but that's the other thing. These super caps will last a long time. That's 5.47. So you can see how it looks like two cylinders that are put together, and I can kind of feel like a little card or something. There's something hard there in between, but so the two center legs are put together, and then the outside legs are coming up. So that's the way it looks. Okay, now this is the guy with the low ESR. This guy's ESR is about 0.2, 0.3 ohms, and this guy's about 50 ohms, the button cell. Okay guys, so what I'm going to do is I'm going to just kind of explain how you get there. You go into this auxiliary menu, and it comes up with this list, and you just choose battery, and once you're there, it's really easy. There's a voltage range, 36 volts, you push it again, 150, push again, 36. Now go to current range. Once you select it, you go 5 amps to 30 amps. We're going to stay in the lower setting for both, since we're only doing like 3.3 volts at real small current, and it's in constant current mode right here. And over here it's set for 5 milliamps. You can use these kind of buttons, well, just like I'm doing there. So you can choose these arrows here to move the cursor around and move this wheel and push it in. You can select that way. But what we're going to do is I'm going to go over here, put that back to 0, and then I'll go here for 5 milliamps. Okay, push that in, select it. All right, now there's a V-stop 2.3. You go to page 2, and you just go to V-stop. It's turned on, and then you can set the voltage. I set for 2.3 instead of 2.5 like I said before. So we'll go down to 3.3 to 2.3, I guess. You can do a charge stop if you had a battery where you're looking at so much charge, or you can even do a time, like do it for a certain period of time then turn it off. But we're going to have the guy shut off at a certain voltage. So you can see the leads are connected right here, running over to the capacitor. Okay guys, so I think we're ready to go. I'm going to put the banana jack into the meter or into the power supply. Okay, so okay guys, I've connected up the power supply, and you see a little current here, and you see just a little bit of voltage there. But look at that, 5 milliamps with only 0.03 volts. It's trying to charge that thing already. Okay, let's bring it up to 3.3 volts. So we're going to be watching this power supply for it, and from here we'll see the current. Now since I'm bringing up the voltage slow, because I don't want to go over voltage on this thing. Alright, so we're about 3.3 volts, and look at the current, still charging that cap. Okay, now just an example, I'm going to pull out the lead out of the power supply. It says it's charged at 3.3, right? But we see current. So when I pull this out, look how quickly it drops below 3. So plug it back in and let's charge. I think we're going to wait until that gets less than 1 milliamp of charge current. And I'll speed this up on the camera. Okay, so we're about 1 milliamp of charge current, and you notice we don't have the load turned on still, right? 0 amps. Okay, now I'm going to pull the lead out of the power supply, and let's see if the voltage stays up. Alright, stays up now. See, it just dropped slightly. I'm going to go ahead and plug it in just for a moment. Let's get it down just a little bit more, because see, it's obviously still charging. It dropped down as soon as we removed the power supply. Alright, I think that's low enough. Let's go ahead and remove it, and then I'm going to turn on the load. Okay, now when I turn on the load, we'll start the timer. See, you can see 5 milliamps almost. It's about, there's 4.8, 5 milliamps. And look at the voltage dropping. Okay, I'm going to just keep quiet and we'll speed through this. All right, battery test complete. So let's go ahead and say okay. And it stops at 2.5, but see, once we stop, that current going through that equivalent series resistance actually has a little voltage drop. So once it stops, the voltage actually kind of floats back up because there's no voltage drop across the ESR. But no current flow. All right, and it took 52 seconds to discharge. All right, so I'm going to go ahead. This is a button cell, right, with about 50 ohms ESR. I'm going to go ahead and just push it in. And see, we've got a pretty good charge at 2.6 volts. I'm going to go ahead and just push in quick and then remove it again. See, now that our power supply is set, I don't have to slowly adjust it. So watch this. Okay, 3.3. Take it out. Drops right back down. Now watch this current, how high it jumps. Here we go. Jumps up and goes down. But now the battery's it's charged about halfway. So you can see how that kind of works, right? Now, I'd have to discharge the battery so we could watch it fully charge again. I'm going to go ahead and do that. And when you discharge your battery, shorting leads together, if you short the leads together like this and discharge it, you got to hold it because look at this current. It takes a while to discharge. That ESR doesn't let it discharge fast. So if I let go, okay, I'm going to let go and watch the voltage on the meter pop up. See this? It bounces right back up to about 0.7 volts already. 0.8. Okay, I'm going to go, it's almost a volt, so I'm going to discharge it again. So these are some of the tricks to know about super capacitors or ultra capacitors. By the way, I might accidentally say battery instead of capacitor once in a while because sometimes I think of them that way. Okay, so it's mostly discharged. When I let go, you see how it jumps up about 0.2? So I'm going to go ahead and I'm going to pop it in the terminal and watch it jump up to 3.3. But look at this current. See how high it goes. Should we do a max hold? Let's capture the max. Wow, it's auto ranging. I just pulled it right back out. It's auto ranging, so it went out of range. I wonder if it went out of milliamp range even. All right, guys, so what I did is I moved that over to the 10 amp range and put that in the amps. Then we're going to turn on the max. And now I'm going to pop this in and see what we can get for peak charge. It looks like only about 69 milliamps. I didn't need to go to the amp stage. That got us up to 1 volt. Let's see if I can get another peak charge. That looks like about the highest current I'm going to get. And the minimum during that time was 28. Max was 0.69. All right, so there's the button cell that we were just working with. Just put it right there. And this is the new cell that we're hooking up. Okay, I've just hooked one up. Let's go ahead and plug it in and see how, here I'm going to see if I can capture max again. There's no charge on it, so let's see how high it goes. Oh, we over limited again. You know what? I'm going to try that amp scale again. All right, got it on the amp scale. Let's try that again. And got it on max. Here we go. And we're charged 1.3 in that quick little charge. That's how this lower ESR allows it to charge so much faster. Look at that, 350 milliamps. Now, we're still charging, but here, let's go to min. Whoops, I guess min was 0. Okay, let's turn off that. Yeah, we're pretty low charge rate right now. It's all charged up, it looks like. Okay, I'm going to switch this over to milliamp range again. Yeah, look, we're down at 1.5. So this type of capacitor charges much quicker. Let's it get below 1 milliamp, and then we'll see how long it stays charged. All right, let's go ahead and I'm going to pull out the power, and you'll see the current drop down to 0. We're not charging. The voltage is sitting at 3.3. Okay, let's go ahead and hit the load on. Okay, we're about 5 milliamps. I'll speed through this. Okay, battery test complete. See, all right? And there it floats back up above. Well, not too much. See, it quit at 2.3, and look, it hardly floated up at all. So the low ESR allows this one go right down to the shutoff voltage, and it doesn't drop very much voltage on the internal resistance, so therefore it doesn't really float up. Like it's 2.32, so maybe 0.02 volts. All right, so I'm going to pop it in and charge it and see how high we can go again just one more time. Now we're already charged at 2.3, so it probably won't draw a ton of current. Let's see. Well, it went over, I think it's 300 milliamp range, so I think it's going just over that. Okay, let's just try it one more time. I shorted the leads together. It only took a few seconds to drop it all the way down to 0.16 volts, and we're going to capture max. I'm in the amp scale, so let's see if we can get a peak charge. Well, about the same as before, 350 milliamps. Now look, it's only been charging just for a few seconds. I'll remove it, and it's all charged. So yeah, this capacitor package, this guy right here, charges and discharges pretty darn quick. Well, with the short discharges, but it actually holds a charge pretty well. So that was a 0.47 farad, and that was a 0.33 farad. So not exactly the same value, but not too far off. Hey guys, so what do you think of that? That was pretty cool, huh? Hey, oh, before I go on this, hey guys, hit the thumbs up. That helps a lot. It helps me with the YouTube stuff. And subscribe if you haven't done so. That'd be awesome. I'd like to know your comments and your ideas and suggestions. Maybe I had to get some of these other caps and maybe try them in some circuits. Maybe see what I can do about replacing some batteries and something. I've seen where people make some huge capacitor banks to replace batteries for like motorcycles and that. Now, that would take a little different cell than what we have here, but maybe I should get some of those. What do you guys think? Pretty cool. Hey, just a few things about cost. Some of those real big ones I'm talking about, they're like 40 bucks a piece, and I'm sure that there's bigger ones that cost even more, but Eaton has, you know, big range of them. I was just looking at some big Eaton's big ones. The little button cell, I think single quantities, that's like $3, a little over $3. That other one with the 2-cylinder, those guys are like $1 more for about the same farads, you know, 0.47, 5.5 volt. So the little button ones and these cylinder, or the oval shaped ones where there's 2 cylindrical capacitors put in series, those guys are all rated for, you know, 5 volts or 5.5, and the rest of these are rated for like 2.7 or 3 volts. Like these are 3 and these are 2.7. Pretty cool caps. So when you see a super cap or an ultra capacitor, make sure that it has the ESR and all those other parameters that maybe, you know, you're only thinking about the farads. Make sure it has those other things work for you too. All right, hey, thanks for watching. See you next time.